Welcome to this talk on Clockdrift in distributed embedded systems. I'm Wenzel-Benner, presenting this material to you. This talk is the English version of a talk we originally gave as Gliwas at the Embedded Software Engineering Kongress 2023 in German language. In this talk, I'm going to describe the problem of Clockdrift to you, the general solution approach, which is called clock synchronization. We will take a look at two established standards for synchronization, and I'll also introduce you to a lightweight approach for which we built a demonstrator. Let's take a look at the problem. Imagine a distributed system with 5 nodes on a network or field bus. Each node contains its own timer counter unit, represented as a clock, showing 3 o'clock, and its own clock source, which is usually a crystal resonator. The nodes together fulfill a function by cooperating, for example, distributed control of gates in a shipping facility. Now, after a few hours of operation, each node opens the associated gate simultaneously at 7 a.m. But we see that in reality this is not exactly simultaneous, and if you look closely at the clocks on the nodes, they are not quite all at 7 p.m. at the same time. That, of course, is not what we expected the system to do. Now, is the problem really that bad? Let's take a look at the real hardware for a while and see how it develops over time. In order to demonstrate the effect of clock drift over time, we set up a demonstrator using 4 Raspberry Pi Pico boards. All Picos contain identical software, which turns the onboard LED on and off at fixed timer values. On the top left is the output from a logic analyzer, which shows the LED signals. Each Pico has its own crystal that drives the timer. The total recording time was over 30 hours, small parts of which will be shown in real time and slow motion. 6 hours. At 6 hours into the experiment, the LEDs still look fine to the naked eye, although a small deviation is already visible on the logic analyzer display. The LEDs no longer turn on at precisely the same time, like they did when the Picos were initially started. 12 hours. After 12 hours, the LED pattern looks almost like an animated light running from right to left. Slow motion clearly shows the right middle left sequence, as does the logic analyzer. Although that one reveals that the second left red Pico is actually ahead of the second right green one by a tiny amount. 24 hours. After 24 hours, the drift of the rightmost Pico got so large that the trigger point of the logic analyzer had to be moved from 50% to 90%. With a now established yellow, red, green, blue flashing sequence, the eye does not get an artificial impression of motion anymore. The rightmost yellow Pico has drifted 400 milliseconds from the leftmost blue Pico, so it is approaching a point where it flashes exactly opposite to the leftmost board. 30 hours. The yellow LED on event has left the logic analyzer buffer, and the yellow LED off event is right on top of the blue LED on event. Rightmost and leftmost Pico are now flashing inverted patterns. One is on when the other is off. Since the LED is turned on by software for 500 milliseconds, this deviation over 30 hours works out to 4.6 ppm clock rate difference, between the leftmost and rightmost pico. This is a typical result for general purpose crystals, even when operating at the same temperature as in this setup. Any temperature difference between the picos would make the impact of the problem much larger. Now that we've seen what happens in the real world with microcontroller boards and their crystal oscillators, what kinds of applications are affected by this problem? What if you are not exactly in the gate opening business? Any application X that collects sensor data, say on node 1, every 10 milliseconds, and sends it to the others for processing, where they process the data every 10 milliseconds, will just chug along nicely, and then sometime at 3 a.m. in the morning, this happens. The reception of fresh data shifts slowly versus the calculation using that data, and eventually the same sample is used twice, or a sample might be dropped. That is pretty enraging. As we've seen in the real-world example, the cause for these issues is the deviation of the crystals from their nominal clock. The nominal clock is the clock rate at which they are supposed to run, the clock rate that is on the label when you buy a type of crystal. Here in this simplified diagram, we assume we have crystals with 1 million cycles per second, aka 1 megahertz. That is the nominal frequency. But the reality is crystal number 2 runs at 1,020,000, so it's 20 cycles per second too fast, whereas crystal 3 runs 20 cycles per second too slow. If we let that system run, assuming they're perfectly synchronized when we power them up, exactly at the same moment, even after just 7 seconds, these two nodes will already be apart by 280 cycles. The principal solution is that all timers involved in the network readjust to one reference timer periodically. This can be done very simple, as described here, or more cleverly, where a rate deviation over time is estimated. But to explain the principle, this is enough. Assuming that every 3 seconds we are able to force this readjustment, we see how timer 2 and timer 3 start to drift apart, but are then forced back to the correct values at the 3-second mark and at the 6-second mark. And in this example, that means at the 7-second mark, where we used to have 280 timer ticks difference, it is now only 40 timer ticks. And it will never grow beyond 80 timer ticks. That is much more acceptable for a working professional system. Now let's take a look at established, available standard protocols. The first established protocol I'd like to introduce is the Network Time Protocol, or NTP for short. It's an internet standard since the 1980s. Its goal is the synchronization of computer clocks, the point being the clocks on different computers in a network shall be synchronized so that it's good enough to compare log files from different computers and get a sensible overview of what is going on in your network. It's already integrated into all modern PC operating systems. It's just there on Windows, Linux, Mac OS, FreeBSD and whatnot. The typical precision that can be reached is 1 millisecond when running on a local area network, and somewhere in the tens or hundreds when running over internet. The other established protocol I'd like to introduce is the Precision Timing Protocol, PTP. This is not an internet standard by the IETF. Instead, it's a measurement system standard by the IEEE, and it's been standardized in 2002. The current version is IEEE 1588-2019 from, you guess it, 2019. The goal here is the synchronization of timers in measurement and control applications. This is supposed to be good enough for high-speed trading, mobile networks, distributed real-time control. and it works best with hardware support built into the Ethernet MAC stage and integrates nicely with modern Ethernet extensions like AVB or TSN. It is precise to less than a microsecond when operated over a local area network. Putting up a comparison of those, we can see that it doesn't really get much more precise than PTP. Any potential do-it-yourself solution will not be substantially more precise. NTP, on the other hand, works very well over internet and is very well tested and widely used. Both, however, come with a significant code size, and both need bidirectional communication and also assume symmetrical delays on the communication line. So a DIY solution can make sense for small microcontrollers and projects if you don't have PTP-enabled Ethernet controllers in your project and the NTP codebase is just too large, or you have a network that just features a semi-directional or simplex transmission. Now, how would one go about deploying such a lightweight approach? Luckily, there is high-quality literature available. We at Gliwas worked very well with this paper from Technical University Darmstadt, Accelerated Clockdrift Estimation for High-Precision Wireless Time Synchronization by Andreas Engel and Andreas Koch. Engel and Koch describe a solution for wireless sensor nodes. So their application uses radio communication, which is battery powered. They have to make do with low processing power and small memories. That leads to a very compact code base. The full theoretical background and the worked out math is available in the paper. The paper is available for free on the university's website. No paywall. It's public tax-funded research and can be easily found by just searching for the authors and the title or using a search system for academic papers. Now, employing the techniques from that paper on a low-cost microcontroller, as we've seen before in the drift situation over a prolonged period of time. How does it look? What can it achieve? Let's see. This setup shows the impact of temperature variations and synchronization using the drift estimation algorithm from TU Darmstadt at work. It comprises the same picos as before, but logic analyzer setup is slightly different. The time resolution is now 500 microseconds per division, and the channel colors from left to right are brown, red, orange, and yellow. The picos are freshly powered up, and the logic analyzer shows all of them flashing their LEDs inside a 2 millisecond window relative to each other. The leftmost brown switching its LED acts as the trigger point, and it will become the sync master once the drift estimation is turned on. All other picos can be seen drifting to the right at different rates. Warming up the red picos crystal by touching it changes the clock rate enough to make that pico drift to the right relative to the others. Touching the brown master picos crystal does not cause any movement of the brown signal, since that is the trigger signal for the logic analyzer. Instead, due to the brown signal drifting to the right, but by definition showing up at the trigger point, all others start drifting faster to the left. Turning on the synchronization using the drift estimation algorithm from TU Darmstadt, all LEDs start switching at the same time. Changing the resolution of the logic analyzer to half a microsecond per division reveals a small amount of jitter. Touching the red crystal shows the tendency of the red pico to drift to the right, but the synchronization, which updates once per second, brings it back in line. If you have any questions left after seeing this presentation, I encourage you to visit our website at www.gliwa.com, or more old school, maybe just read a good book on embedded software timing. Especially Peter Gliwas' book is available in many languages, and probably you should find one that suits your needs.